Okay, this is MAC1114 and this is section 9.5. In this section we are learning some operations having to do with vectors, which we looked at in section 9.4. Specifically, we're looking at how to find the dot product of two vectors, which is the first formula that you're seeing, as well as some other algebraic operations that we're going to talk about with regard to vectors. Also, we're going to look at some applications that require the use of the dot product, so kind of the focus is on that in this section. Okay, so in number 1, we're learning how to find the dot product, which is really just multiplying vectors, and the formula is right here. It says if you have two vectors called u and v, you multiply the horizontal components, which are the front numbers. Then you multiply the vertical components, which are the back numbers, b and d. Okay, so these are the front numbers multiplied, A and C. These are the back numbers multiplied, and then you add them. It's as simple as that. To show your work, they use a big thick dot rather than the normal one that you see. And you can put your vectors right here just to show what you're multiplying. And the work that comes from the formula. So it's front times front. Those are the vertical components. And then you're adding that to the back components multiplied together, which are -1 and 3. Okay, this turns out to be -12. This turns out to be -3. Final answer, -15. By the way, this is called a scalar, a number that is just a regular number rather than a number that has two elements that belong to it, like a vector or like a point. So this is what we call a scalar. Okay, so that would be the answer. Then there are various things, applications that you can use this dot product in, like finding the angle between two vectors. So like for instance, that's what you're asked in problem number 2. And just to give you a visual on that, although you don't have to draw it just to get the answer, you could jump right into the formula, which is this right here, where you're doing a dot product on the top. That's what that says. Your numerator is going to be a dot product. And then what they're asking you to use in the bottom are the magnitudes. So this would be the magnitude of u, this would be the magnitude of v. And if you have forgotten what a magnitude is from the previous section, let's just say that the vector u has these two components, just so I can remind you what a magnitude is. If this vector right here had the a front and a back component, all you would do to find the magnitude, or what's called the length of the vector, is to square the first component, square the second component, and add them together and take the square root. You're going to be doing that for both of these vectors and multiplying them together. Okay, so just again to give you a picture of what you're doing. If you were going to, draw a picture of the vector 2, 5, basically like you're plotting a point. So 2, 5 would be right here. And then -4, -1. 1, 2, 3, 4 would be there. So this would be u, this would be v, and all you're doing is finding the angle that's between them. No need to find reference angles or anything like that, because all you're doing is finding the angular space between the vectors. Okay, so using the formula that they have for you right here, I just explained what's in the numerator and what you're doing in the denominator, so let's go into more detail on that. So the theta is the last thing that we'll be finding. We have to set up all the numbers on the right-hand side of the formula. So the dot product would be dot product of 2, 5 times dot product of -4, -1. And then I'll go ahead and set up the bottom as well and then start working on simplifying it. So the magnitude of this vector 2, 5 would just be, or the length of that vector, which is what the magnitude is, would be like that. That would be 4. This would be a 25. So you're looking at one magnitude being the square root of 29, and then the other one that has components -4 and -1, that would be -4 squared plus -1 squared. Okay, so that would be 16 plus 1, so the other vector has a 17 underneath it. If you want to combine these into one radical, which you can as long as the indices are the same, they're both square roots, and that allows you to bring them up under just one radical. Okay, so what you are, and let's see what we have on the numerator as well, because then we can begin to get a decimal for it. So the dot product, I haven't done that yet. I was doing all this work on magnitudes and finding their product. So that's what I have on the bottom. And then the dot product in the numerator, front times front, plus back times back. So this is -13 divided by square root of 593, and you can go ahead and put that into your calculator. Let's hold on to at least 4 numbers after the decimal. I believe that is -0.5855, rounded off. Remember, all of this that you've done, that's what cosine of theta is equal to. So you're at this point right now. Then if you want to finish that problem and actually find theta, which is what they asked you for, find the angle between the vectors, so that's the theta. You have to turn this around and do what you always do. Find an inverse. Inverses are for finding angles. So -0.5855. You're finding it in degrees, and they've asked you to find it to the nearest tenths place. Okay, so let's go ahead and put that in the calculator. And I believe that comes out to be 125.8, rounded to the tenths place, and you're in degrees. Okay, so that's one application of using the dot product. Let's move on to the next page, where we look at another application of the dot product, which is using them to figure out whether lines are parallel or perpendicular or neither. Okay, when they are perpendicular, then this will follow. Dot product will be equal to 0 when they're perpendicular. When they're parallel, what happens in that case is that one vector will be a multiple of the other. One vector is the other vector multiplied by some scalar. And if neither one of these are happening, then they're neither parallel nor perpendicular. And you can answer the question with respect to how it's asked. Like this one specifically asks you, make a decision about whether these are orthogonal. If they are, that means that the dot product is 0. Because by the way, I don't know if you noticed that here in the what I put by the formula, but perpendicular and orthogonal mean the same thing. Orthogonal is the word that they use when you're talking perpendicular, but with respect to vectors. Okay, so we're going to find out, to answer this question, whether or not the dot product is 0, because if it is, then that means it's orthogonal, and if it isn't, the dot product isn't 0, then we'll say no, it's not orthogonal. So let's go ahead and do the dot product. I don't need to write these vectors again. I can just jump into the actual formula. So dot product from the first page is front times front plus back times back, so that you're multiplying the horizontal components or the front components, and you're also multiplying the back components or the vertical components. This turns out to be -16. And then in the back, let's make sure we have everything right. 4 times -4, -1 times -16. This turns out to be positive 16, which is 0. Therefore, that's what these 3 dots mean. 3 dots shaped like a triangle. Therefore, the vectors are orthogonal. Okay. All right, then this one, determine whether they're parallel, orthogonal, or neither. Now, if they are orthogonal, as we just saw in this problem right here, when you do the dot product, you will come out to be 0. I don't believe that's going to be the case, but just so you have a little extra practice right here, I'll go ahead and show you that that isn't the case. So if we were doing the dot product, we would go 6 times 3. Those are the front components, the horizontal components. And then the back components are -8 and -4. And you can probably see what's going to happen here. You get an 18 for your front product. Now, if they are perpendicular, orthogonal, then this dot product should come out to be 0. But you can see that that is not happening. And instead, what you get here is a 50. So they are not orthogonal. But let's see if they are parallel. Okay, now if they are parallel, then that just means that you can take one of the vectors and multiply it by some scalar to get the other vector. You might want to go from the smaller numbers to the bigger numbers just because you won't have fractions, but either way, if you were to take 3, -4, is there something that you could multiply both of these components by in order to turn it into 6, -8? These numbers are very small, and it's easy to see that 2 is the number, the scalar, that you could multiply both of these components by to get these. So, since there is a number, and again, whether that number is a fraction or an integer is irrelevant, if there is some number that you can multiply both of these components by to result in the other vector, then that means they are parallel. So therefore, the vectors are parallel. Okay, this is the answer for that one. Okay, then here what you're doing is just kind of reviewing everything that was taught thus far in numbers 1 through 4. So this number 5 is a review, just practicing everything over again. Here we go. Part A, find the dot product. Now you see that this time the vectors are written in IJ form, and you're welcome to leave them like that. You can leave them like that, or you can write them in component form, which I will review with you so that you know you have options for the way you show your work. If you want to write this vector in component form, it would just be 3, -4. And if you want to write this in component form, it's -6, 8. So just kind of like a shorthand way of writing a vector. Now, it's not necessary. You can jump right into the dot product even when it's in the IJ form. Okay, so just like with the component form, you're going to go front component times front component. Those would be the I coefficients. So 3 times -6. And then you're going to multiply the back components as well. Or in other words, taking the coefficients of the J terms. So that would be -4, that's the number in front of this J, and 8 is the number in front of the other one. Remember, your dot product always comes out to be a scalar. It doesn't have I's or J's, nor is it in component form. So this is going to be -18 for the first product. Second product is -32. When you add those two together, you get -50. So that's the first answer. Part B, which I'll do right down here. Part B, find the angle between vector V and W. So that formula starts off like this, cosine of theta. Theta will represent the angle between the vectors. You're doing the dot product on the front, at the top in the numerator, and I'm going to write it in component form as I showed you right here. I just think it's neater when you write it that way. rather than carrying around the i's and the j's. But either way. So I'm going to be doing that in my numerator, and then in my denominator I do the magnitude. So the magnitude for this vector would be 3 squared plus negative 4 squared. And then the magnitude of the other vector would be negative 6 squared plus 8 squared. Okay, and if you want to just keep working on the denominators, you can do that, and then we can go and do the top. Okay, so this would be 9 plus 16. That means you have a 25 underneath this radical, which means you have a 5. And then you're supposed to be multiplying that by whatever you get for the magnitude of the other vector. So this would be 36. This would be 64. And then when you add those together, you end up with 100. Square root of 100 is 10. So on the bottom, 5 times 10, 50. Doing the numerator now, which asks for the dot product, it's front times front. And I guess I'll write that out so I'm not skipping steps with you. And back times back. Negative 4 times 8. Okay, this ends up being negative 18. This ends up being negative 32, which I don't know why I'm doing it again. I didn't need to do that because I already had this answer from part A. So I did a little extra work. So anyway, this turns out to be negative 1. Okay, part C. Oops, I didn't finish. So if right now you know that the cosine of theta is equal to negative 1, but yet your whole thing was that you were being asked what is the angle in between the two vectors, then you have to continue. So right now it's cosine of theta is equal to the calculation that you got here, and after doing all this work, turned out to be negative 1. So if I want to know what the theta is, then it's inverse of the negative 1 value that you got, and you can put that in your calculator. But the place at which cosine, the theta at which cosine is negative 1, but again, you can put it in your calculator. Make sure it's in degrees, and you can then write it in pi form if you want to, but this happens at theta equal to 1 pi, or in other words, 180 degrees. You can give either one of those answers unless my math lab stipulates a particular answer. Okay, so this is the final answer for part B. In part C, state whether they are parallel, orthogonal, or neither. So in part C, let's see, those vectors were 3, negative 4. I'll just bring them down here. And the other one was negative 6 and 8. And you just ask yourself, I mean, these look like they're parallel. Could I multiply both of these to get what you're seeing over here? And you just have to check it out because it could just be a matter of, they may look like they're parallel, but maybe they're not. If you were to just use a 2, because you could use a 2 and turn this into a 6, but it would have to be a negative 2. Does that work? So you see that that times that is negative 6, and this times that is positive 8. So I get both of these values when taking the components of this vector and multiplying it by negative 2. So therefore, these vectors are parallel. And again, that's because this scalar times the two components equals the other one. Okay, that's parts A, B, and C. Last problem on this section, and the last section of chapter 9. So all the way done with the 4 chapters in this class, 1 section left to go, which is a section from chapter 10. Okay, that'll be in the next video. But to finish this off, we're going to deconstruct a vector into what's called its parallel and orthogonal vector components. Okay, so the decomposition of V into vectors V1 and V2, where V1 will represent the parallel vector to W, and V2 will represent the orthogonal vector to W. And they give you formulas for it right here. So and you're welcome to write these in component form if you want to work the problem with the vectors like that. V would just be 12, 4. I just have a preference for that. And then W would be negative 1, 1. But, as I said, not necessary. So following this, if you want to find the parallel vector, which they've talked about right here, V1, and they've given you a formula. So V1 is going to be the dot product, and I'll go ahead and write out the numbers that we're going to use. So that's going to be 12, 4, and we're going to do a dot product of 12, 4 with negative 1, 1. And then on the bottom, we're going to do the magnitude of W, and we're going to square it. So the magnitude of W and square it. So let me just jump into the arithmetic that goes with it. Here's vector W. Magnitude, if you have been catching on to what I did in the previous problems in this section, it's just front component squared plus back component squared. Okay, so that would be negative 1 squared is 1, 1 squared is 1, you'd have a 2 right here. But the formula says that you're going to take this magnitude of vector W and you're going to square it. So you're going to take this and square it. So what happens is when you square a square root, it cancels the square root. These two operations undo each other and out comes the 2. On the dot product, and don't forget I have not written one part of this, so let me make some room right here. You're doing the dot product on the top, which I'm about to do. You're doing the magnitude squared on the bottom, which I've already done, and you're multiplying it by vector W. Let me move this over a little bit so I'm not cramming everything together. Okay, so let's go ahead and do the dot product, and then we'll write the vector W right next to it. Okay, so it's front times front plus back times back times vector W. And vector W is negative 1, 1. This is what we have to do to finish this problem. Okay, so continue moving. I'll do it right down here. Let me check this out real quick. That's negative 12. That's 4. Those two added together is negative 8 times the vector negative 1, 1. You have a 2 down here. Now, if you want to, you can reduce what you see right here, these coefficients, which would be negative 4, and then you can bring that into the components of the vector. So this would be, and this is one of the algebraic properties that are on the first page, so you can distribute this scalar into the components. So this would be positive 4 now for my front component, and then negative 4 times 1 on the back would be negative 4. So what you have just found is you have found a parallel vector to W. Okay, this vector is parallel to the vector W. Okay, so this is one of your answers. Then the other thing that you've been asked in this problem, not only to find the parallel vector to W, but also to find the orthogonal or perpendicular vector to W. So there's a formula for that also. They call the orthogonal vector V2. And you have a formula there for it. Okay, so this would be the vector v minus vector v1. And this was vector v1 that we were doing all this work for right here. Okay, so following this formula for the orthogonal vector, it's the vector v, which is 12, 4, right up there at the top, and then you're going to subtract what you got for the parallel vector, which is 4, negative 4. Okay, more algebraic operations on vectors. Also in the tables that were presented on the first page, it's just front minus front component, so 12 minus 4, and then back component minus back component. Okay, and this is going to be an actual vector, not a scalar, not a singular number, two quantities here. So the front component would be 8. This is just my work. This would be 4 plus 4, 8 also. Okay, and this is the vector that is orthogonal. To vector W. Okay, so we did the parallel vector to W and we did the orthogonal vector. And that's it.